right, guys. All right, as you can tell, welcome to another IAEI News Live. I've got some throat issues going on right now. I am had an allergy attack, and so I'm popping a bunch of these. I don't know what they're called. Rue Boys things. Where's my glasses? I'm missing my glasses. Where's my glasses? There they are. All right, guys. Hello, Laurel. Welcome. And I am Ricolai. Popping Ricolais. And I hate the spring. That means all of the pollen's out, all of the mold and mildew and all that good stuff. Let's see who we got going on right now. But remember, IAEI News Live must go on regardless of whether or not I can talk. Okay, alternative preventative saying to the intent to prevent a rapid, absolutely unintended, or something like that. A rapid, unintended disassembly in the field. That's the key, David. There we go. We are on, Robert. Robert is in the house. Available fault current syndrome that it took my appointment as a plans examiner in 2005 to finally get my head into it, to fully understand what it was all about. So today's topic is all about available fault current. So what we're going to do, and I know we've dug into this before, but you know what? Here's the thing. Here's the thing, David. The IAEI's YouTube channel broke 10,000 followers. Yes, 10,000 followers. We have put 10,000 in our past. And that is awesome. It's because of everybody out there sharing, communicating. We are a force to be reckoned with. So, Robert says, Robert from Omaha, morning. Steve in the house. Rapid, unintended, rapid disassembly in the field. And that is ungood. Technical term. Look it up in the Dimitrovich Library of something. All right. Felix Sandoval in the house. Unintended rapid disassembly in the field must be a defined term. You know what, Felix, so here's the thing. If we're going to define the term, we have to use the term. So what we could do is put that terminology into Article 110.10 or the definition of what a short circuit current rating is. It's the beyond which, or no, we'll put it in the definition of fault current. Michael Hofkin in the house. Thank you. Hey, I'm feeling Jason. Telling you what, buddy. I've had so much going on up here. Right now, it's all in my chest. And whoo. Paul Bunbury, Santa Rosa, awesome. Man, wait, Keith Wilson, thanks for joining us, Keith. Good afternoon, good morning, good evening. Yeah, Paul, thanks, man. I need it, brother. And we got Joseph Violi. We have Redondo. Thanks, Costa Rica. You know what I need? More coffee. That's what I need, more coffee. And you know what? Here's the bad part. My coffee cup is empty. So I need more Costa Rica coffee. All right, we got Don Ganier. We got Felix. We got Carl Lewis. Good morning. Hopefully we talk. Yes, Carl. Talk about arc flash. Ah, we can. Yeah, you know what? We could. We could definitely do that. And another get better. Thank you very much. All right, so let's get into our discussion. Brian, Byron. Oh man, I love it. Byron Kroll. So let's talk about this now. Whoa, not per unit. We're going to get to per unit. But I want to talk short circuit currents first. Okay, so what is a short circuit current? A short circuit current is when the current goes outside of the normal path. So if you think about a circuit, and you have a circuit breaker back in your panel board, you have current coming out that hot wire, the black wire, like in a residential dwelling unit, from an NM wire perspective, it comes out that black wire and it comes back the white wire on a single phase 120 volt circuit. So I have a hot conductor and I have a grounded conductor, ungrounded conductor, and a grounded conductor, and I have a load at the end. As long as current stays in the path, any current that exceeds the rating of the conductor or the equipment is an overcurrent, is an overload. Because remember, overcurrents are all encompassing. I have overloads, I have short circuits, I have ground fault currents. Those are all overcurrents. Check that coffee. Yes. Need your coffee, buddy. So, let's go back. So we know, and you know, a lot of times what our challenge is to describe fault current in sometimes to those who are not electrical. So Donald Beeman, back in 1930 something, I think, I can't remember, 1930 something. I was just looking for my book and I don't have it. In fact, I don't even have my code book, but I'll use NFPA link. So Donald Beeman described short circuit current this way. That, hey, Freddie B, when you have a fault, when you have a normal condition, if you liken it to a dam, water naturally passes through this dam in a controlled manner. The flow of water from the reservoir to the stream down below is controlled and managed. But if the dam breaks, current is now going outside of the normal path, and destruction occurs to everything in its wake. So that water has a force behind it, and the amount of force could be the potential. The amount of volume of that water could represent the voltage potential that's driving current through a circuit. You'll get more current if I increase the voltage potential. I'll get stronger water flowing out of the Boulder Dam than I will out of this Beaver Dam that I have down the street. Okay, when I break them. So I got people texting me and all that good stuff. So why do we calculate fault currents? We calculate fault currents for various reasons. I will calculate a maximum available fault current to do equipment evaluations, we have to make sure that in a power distribution system, say a power distribution system like this, that diagram appears to be what I observed in the plan review document that taught me about available fault current. Yeah, that diagram has been around for a long time, David. And my first introduction to the dam, to that whole concept, was through Donald Beeman's Industrial Power Systems Handbook. Really great reference that I read when I was in college. A very important reference in my opinion. Eric Hammond in the house, welcome. And a Tech Tuesday would not be the same without you, buddy. I don't know if you heard, Eric. We broke 10,000 followers on IAEI's YouTube channel. We are skyrocketing through the ceiling. We are blowing it out the house. We're kicking butt and taking names here on IAEI News Live. So, where was I? Oh, so when you think about this power distribution system I'm showing here, and I might have a motor down here, and hopefully a better drawn motor than that, right? So you might have motors, you might have panel boards that then supply other equipment. You may have, let me draw a light bulb. So you may have lights, lighting, whatever it is. Thank you, Eric. Appreciate it. Hey, Travis Holderman in the house. It wouldn't be a Tech Tuesday without Travis either. Thanks for joining in, buddy. So, I apologize for my voice, but can't help it. It is what it is. So, when power will flow, I'm gonna cross this out, and we'll call this a utility. Okay, so power is going to flow naturally down through this system, down through here, all the way down to the loads, and it's going to flow and provide power in a normal environment. But when I have a fault, if I assume a fault occurs in the system here, I'm going to have an abnormal situation. I'm going to have remember what happens during a fault. If I have 3 conductors, basically, I could be taking all 3 of those to ground. I could just be shorting all 3 of those together in a 3-phase system. In that case, all the current is coming to the party, and it's unattended rapid disassembly right there, right? So what you have to think about is all of this equipment has to carry and deliver the fault current to where the fault is. And there will, if, which we did draw earlier, we drew a motor, right? We drew a motor. That motor could contribute fault current back to the system. And in fact, here we go. And then, and I know you guys like videos, so life would not be good without a good video. Let's take a look at what happens. This is why we calculate fault current, because we want to apply. We want to make sure all of these circuit breakers, have the right interrupting rating. We want to make sure this equipment has the right short circuit current rating. We want to make sure this conductor is protected. And you know what that is? That's also a short circuit current rating as well. We want to make sure that this transformer is protected. During fault conditions, every component that is going to carry current has to be able to hold it together until one of these puppies, or this guy, or gal, clears the fault in the power distribution system, however long that takes. So, when you don't do that,
this is a serious misapplication.
whoa.
Again, this is a serious misapplication.
So those are two great Busman videos that I've seen, and I know many of you probably have seen as well, of unintended rapid disassemblies in the field. All right, so that was a demonstration of a short circuit current rating being exceeded. That's not a fault that started inside the equipment. That's a fault. If you look down there, that little black and white zebra-shaped conductor, that conductor is shorted at the end of it. So the fault current passed through the equipment, and the components inside were not able to hold it together under the pressure. It's sort of like being in a shouting match with someone, and you just start to cry because you can't take the pressure. So there are two key sections, and Laurel hit it right. Our research department said it right. Laurel from Omaha, or Laurel in Omaha, identified two key sections. 110.9 is interrupting ratings. So whenever we look at overcurrent protective devices, whether it is a fuse or a circuit breaker, we want to make sure that the interrupting rating is adequate, meaning the rating of the interrupting rating of the overcurrent protective device is greater than the available fault current. Now remember, there's a difference. There's a difference between the interrupting rating and the short circuit current rating. 110.10 focuses on a short circuit current rating. 110.9 is an interrupting rating. Now the difference is that a short circuit current rating, as we said, is the ability of the equipment to let current pass through it and not achieve an unintended rapid disassembly in the field. You don't want that equipment to just come apart because of the magnetic forces. The interrupting rating is the ability of, and I'm going to say, you know what, Laurel? I used to think about this incorrectly in the past. And I'll tell you why. I need my browser. There it is. And I will tell you why. And it's because I need to go to NFPA link And I want to read to you the definition of what a short circuit, an interrupting rating is. Now, interrupting rating starts with the letter I. And what you would have to do is go down in an alphabetical order and look for I's and then go to interrupting. Phew. I got it. Oh, man. I'm having a difficult time today, and it's probably because I'm not feeling good. But that's never stopped me. Interrupting rating. Here we go. All right, you ready for this one? Y'all ready for this? The highest current at rated voltage that a device is identified to interrupt under standard test conditions. So what that means is an interrupting rating is not just about interrupting fault currents. If I have a light switch, for example, and I'm going to turn lights on and off with that switch, it has an interrupting rating. Although it's not a short circuit value, it's a load current value, it is the maximum current at rated voltage that device is intended or identified to interrupt under standard test conditions. Stop the flow of current. So when we calculate short circuit currents, we want to make sure that the equipment is rated to handle it under these fault conditions, whether it's a component that's going to be higher up in the system, that it has to let that current pass through it, supply the fault until an overcurrent device interrupts the flow of that current, right? Or if it is an overcurrent device that has to stop that flow of current. A device that is intended to function on a fault will be tested for those fault currents. Make sense? All right. Thank you, Laurel, for those two references, 110.9 and 110.10. Everybody write those down. Robert from Omaha. Conductor withstand rating should be checked, and when fault occurs, the wire sees the same fault current, yet the wire insulation is not checked. So, here's the thing, Robert. When you look at the National Electrical Code, it gives you guidance based upon a conductor, and it just tells you what size overcurrent device that is needed to protect that wire. It doesn't specify instantaneous pickups or short time delays. It uses, and we don't typically plot the curves for every one of those. If I was going to, for example, if I had a time current, if I had a time current characteristic curve, remember, and on a TCC curve, we have seconds up the y-axis, and we have current here. The damage curve for a conductor looks something like this. Okay, and this is a conductor damage curve. And what we would typically do is plot a circuit breaker. Let's say we plotted a thermomagnetic circuit breaker. Boy, I am the artist, aren't I, Robert? Come on, man. Give me some kudos here. Tommy D's looking for some wow factor right there. You know what I'm talking about. And let's say we cut this off at I short circuit. Right? So now what that tells me is my overcurrent protective device, this circuit breaker, is going to open before the current gets into the damage curve of the conductor. Now, what I showed, in reality, this conductor damage curve is much further to the right on the TCC curve, more so than you would think. So, we got some more comments here. So in any case, that damage curve, there's an equation for it. And it is in the National Electrical Code. And you're protecting that conductor from two parameters. One is short circuit, which we call the, oh my gosh, what do we call that? The, what do we call that? The shorts, you don't want it to, you don't want the conductor to vaporize. And then there's an annealing. But when you think about a conductor, a conductor has insulation, right? You have a copy. I don't know if I can do this, but I'm going to try. I hate when things don't work. Copy. Anyway, I tried. I gave it the old 1-3, but it's not liking me. So, a conductor has an insulation, like a rubber or a compound. It depends on the conductor that you select. That conductor is going to get hot, and what we don't want to do is melt that insulation. So the damage curve has to take that insulation into consideration, and there are temperature for the equation that's in the National Electrical Code. You'll see some key parameters for that information. Dawn says, for a conductor, the short circuit withstand has mostly to do with not exceeding the short-term temperature rating of the insulation. Exactly, typically 150 degrees C. So both current and clearing time come into play. Absolutely. The amount of current, the amount of time, and that damage curve that I showed you is based upon the equation that you'll find in the National Electrical Code. Yes, Robert, there's a difference between the two. Would a light switch have a short circuit current rating? Absolutely, it does. It's funny how, in fact, you know what's really interesting is even a receptacle, short SCCR of a light switch. I'm going to see what we can find. What is the short circuit current rating of a... You know what I'm going to do is I'm going to go and find... we'll do Pass and Seymour. Light switch. Residential light switches from Legrand. Oh. Yeah, there we go. That's a three-way. I just want a regular light switch. I just want to pick up a light switch. There we go. 15 amp single pole switch. Let's see if we have specifications. I'm curious if there's a specifications. Agencies, 15 amp. Number of poles, contact rating, 15 amps. We'll look at the cut sheet. Let's take a look at the cut sheet. And then, what we could do is we could pull up the UL standard. I think a receptacle probably would be easier. But let's take a look at, I'm just calling up the cut sheet right now to see what they might have. And they're not having it. So what I have, I'm just to pick the standard switch, 1 year product width. So you got all that information. It's UL listed. You've got the contact ratings, the number of, you got the wire sizes, and the ampere rating. So let's do this. Excuse me. Sorry. Let's do a quick search for, let's take a look on their same website, GFCI receptacle. Take a look at that. Okay, so now I'm just going to take a look at the receptacle. I'm going to go to specifications, product dimensions, resources, test guide, radiant, pass and Seymour, installation. I'm not seeing there should be a short circuit current rating on here as well. Let's go to Leviton. Let's go to Leviton. Let's take a look at a GFCI receptacle. And let's just look at one of these. And we scroll down, instruction, documents, technical information. Hello. There we go. Look at that. Short circuit current rating is 10,000 amps on this receptacle. And you have horsepower ratings as well. Let's so that shows you that there's at least one manufacturer. I didn't. Let's check light switch. Let's take a look at a light switch. Here we go. Toggle switch. They call them toggle switches. So let's do that. Let's take a look down here. Let's go to instruction, technical information. Ampere, withstand 1500 volts for 1 minute. Grounding, overload, temperature rise, voltage. I'm not seeing anything in here on short circuit current rating. So we could always take a look at the standard, and maybe, Fred, I can do that after a while. And maybe that'll be a good Q&A Friday for IAEI News Live. But if it's carrying fault current, just think about it. That light switch could be at the source of any in the power distribution system. Every component in a power distribution system has to, it's going to carry fault current, so it has to do it safely, right? Will a fuse respond faster than a circuit breaker on the same fault current value? Carl, it depends. So Carl, if you think about a fuse and a circuit breaker, if I drew two curves, let's draw a fuse curve. And let's draw a circuit breaker curve. Ooh, I'm going to use red. Let's draw a circuit breaker curve. And I have the circuit breaker and fuse at the same limit. If I drew these two, I would say for any current greater than this value in this region, yeah, that fuse is going to go a heck of a lot faster than the circuit breaker will. But when you're in this region here, or this region here, the circuit breaker could go faster than the fuse. It all depends on the time current characteristic curve. So I could not answer that question generically. All right, we're going to get back to fault currents. All right, so let's do this. Let's get back to our regularly scheduled program. All right, so we already talked about interrupting rating, and that is a defined term in Article. That is a defined term in Article 100 for interrupting rating. Short circuit current rating is also a defined term in Article 100. Now, the power distribution system. What we would typically do for equipment evaluations is we want the maximum available fault current. So we'll make some assumptions. We'll assume that the transformer is at its lowest possible impedance. We'll assume that all of the sources are on. We will assume all of those motors are on and running. Okay? Because we want the maximum available fault current that could possibly flow in the power distribution system. But what we have to do is we have to convert this into an impedance diagram. Now, some key things you want to think about, or key terms that you're going to need to know. You will see it used. Thevenin equivalent. A Thevenin equivalent is the representation of a portion of the circuit, typically looking up into a system. So if I could, for example, this power system right here, if I wanted to, I could take this entire thing right here, all of that, and I could represent that as this. With a V Thevenin and a Z Thevenin. I could represent that entire network as a voltage in series with an impedance. Simplifying my network analysis. And we may do that on certain occasions, depending upon what exactly my goal is in the system. So, for example, if I wanted to, let's think about this. So Thevenin equivalent. Let me go back. I'm going to finish my thought. Thevenin equivalent is going to be a term. Dadgummit. Wrong one. Thevenin equivalent is going to be a term that you will use, and sometimes you don't even know you're using it. But it's the ability to represent everything in a simple voltage and impedance. Ohm's law is another critical law I'm trying to think principle, fundamental that you need to know. And I know all of you in the electrical industry are taught this from day one. It's the electric current through a conductor between 2 points is proportional, directly proportional to voltage across those 2 points. So voltage is equal to the current times And what I could say is, depending upon what I'm, V is equal to I Z, because Z could be R plus JX, and that's a complex variable. So keep that in mind, that in some cases, I might be replacing R with Z equals R plus JX, a real and a reactive component. The same goes for this, and the same goes for that. Because remember, voltage is going to be at a phase angle, and current's going to be at a phase angle. So I just have to be mindful that when I have a series of reactances, resistances, I'm going to have an angle aspect to this, which brings in the concept of, and we're thinking on the fly here, trigonometry. Let's go to black. Trigonometry. I don't know how you spell trigonometry, but it's trigon. I think it's ETRY. Is it ETRY? Trigonometry. Trigonometry. Whatever. So I trig is very important, and I'll go to and I will speak. I mean, this is another. If there is anything more fundamental than the power triangle, I don't know what is for power systems engineers. So you have your real, and you have your imaginary. This could be X, this could be R, this could be VARs, this could be watts. This is your power factor, and this could be VA. It could be Z, like we were just talking. All right? So trigonometry is another, and then you got your equations. Cosine theta is your x-axis. X-axis, I'll call it adjacent. That's your adjacent over hypotenuse. And then sine theta is opposite over hypotenuse. Tan theta is opposite over adjacent. And I hope I got that right. Or is it adjacent over opposite? I think it's opposite over adjacent. Trigonometry. Trigonometry. Thank you. Salsa. Sound system is now on. Sorry about that. I don't know if I screwed something up there. Isn't a minimum of 5 kA? You know what? Not necessarily. I know a GFCI receptacle that hasn't gone through supplement SA is a 2 kA short circuit current rating. David. What you're calling imaginary power is what we normally call apparent power. Yes. Hold on. Salsa is... Hold on. I thought apparent power was the VA. Yes, it is. All right, so add a page. So if I was going to do a power triangle, this would be watts. This would be VARs, and this would be apparent power, which is VA. That's the way I was always taught. That's the way I was always taught, and I just Googled it over here, and they have this image. They have an image here. I don't know if I can't, but there it is, and they have apparent power. S is equal to VI or IV. So that's the way I was always taught that. Yeah, Jason. Yeah, apparent power is VA. So we're probably saying the exact same thing. I just want to make sure I'm clear with that. So we use this triangle for a lot of things, and what we'll use it for during the fault current analysis is we will have to represent. We're going to have to take this circuit. Let's say that I was going to assume an infinite bus. I would have to convert this into an impedance diagram. So that infinite bus would be a Z. This would be the Z for the transformer. This would be the Z for the secondary conductor. And then I'm at the bus. Now, I could, sometimes we do this, and honestly, I typically would omit it. But if you wanted to do things how we would typically do this, you would also, if you wanted to do it how we would, here's the thing, sometimes I'll take shortcuts. And that's not necessarily a bad thing, because the Z for the infinite bus is going to be pretty doggone low. This could be the Z for the primary conductor. So I would represent, but typically what we would do is basically represent the entire primary of, we would represent the entire primary of this transformer. All of this with a Z Thevenin. And I'll show you the equation for that. But when we say an infinite bus, what we mean by that is an infinite amount of available fault current at that point in the system. Quadrillion, billion, gadillions, whatever you want to call it. It's the biggest number you can think of for fault current. Infinite, an infinite amount of fault current at the source. So I'm not worried about the conductor on the primary of that transformer is my point. So, but that's basically what we're doing. So every component, the transformer has to be, what we typically do with a transformer, you would convert that into an R plus JX, but we assume R is small and irrelevant, and we would just ignore it, and we would just say basically that your transformer is all reactive. It's a big core. It's all reactive. This conductor would have an R plus JX, and the conductor itself, if you go to, let's talk about conductor impedance real quick. Let's talk about the conductor. Where is it at? Oh boy, my throat's really getting to me. All right, so I have some slides on the conductor impedance. There we go. Conductor impedance. Let's talk about conductor impedance. We would typically model both an R and an X, a resistance and a reactive component. So there's your triangle again. You have a real, you have a resistance, and you have an X, an inductance for each equipment. We already talked about the power triangle, all that jazz. So if I go to chapter 9, table 9, you'll see that there is this value. You've got for each of the sizes of conductors, you have a reactance, and you'll notice that there's ohms per kilometer, ohms per 1,000 foot. So the bottom number in this is your ohms per 1,000 foot, right? So don't forget, use the bottom number. Then you have your resistance, and this is for copper wires or for aluminum wires. So you have different values for both. You also have to know whether or not it's in PVC, aluminum conduit, or others. Yes, Eric, your infinite bus is a very good method to calculate the maximum available fault current, because if your short circuit current ratings and your interrupted ratings exceed that value which you calculated, which will never be seen in the system because you've taken some assumptions, then you're good to go, right? So a conductor will have, and then that over there is your effective Z at a 0.85 power factor. And I believe they would typically be able to use that for your voltage drop calculations. And there's some notes to follow up on. So, so you would typically, what we would do is we would basically represent this whole system in a one-line diagram and do a network impedance where we'd say, look, I have on this system, I've got a voltage Thevenin, I got a voltage per unit, which is another term, per unit. Per unit values are actual over base, and if you say, well, I never get into per unit, you use per unit because the percent impedance of a transformer, percent impedance is a per unit value. So you still use it, you just don't realize it. So a per unit is an actual over a base. But we would put this all in a per unit. We would basically then use Ohm's law to add up all the impedances. So V is equal to IR. If I know this is all of those combined together, then I know I is equal to the voltage, which is 1 per unit, over the Z impedance, which is all three of those added up. And then I can calculate my impedance all the way down to the bus, which includes the conductor. If I'm just on the secondary, now if I'm just the transformer, and let's say that I just want, I'm going to forget about the down to the bus, and I'm just going to look right there at the secondary of that transformer, and I'm going to figure it's an infinite bus. So an infinite bus is basically infinite amount, which is a zero impedance. So now I just have this, my voltage and my transformer. How do I calculate the maximum available fault current on the secondary of a transformer? If I knew this was 5.75, I would take if I knew this was 5.75, this was a 1500 kVA transformer, and it was a 480 volt secondary, I take I full load amps is equal to 1500 divided by the square root of 3, divide that by 0.48, What does that come out to be? What does it come out to be? 1,500. 1,500 divided by the square root of 3. Divide that by 0.48. 1804. So that is 1804 amps. I short circuit is equal to 1 over, 1804 over 0.0575. Times 0.9. So the maximum fault current will be plus or minus 10% on transformer impedances. Can't forget that. So 1804 0.0575 times 0.9. Divide those two. 34,864 amps. 34,864 amps is the maximum fault current I could possibly see on the secondary of this 1500 kVA transformer with a 480 volt secondary and a 5.75% impedance. And I'm assuming that I'm on the low end. My impedance is lower on the plus or minus 10% for that transformer. All right. Here's what we're going to do. And another tool, here's a free tool. And I know you guys and gals have probably seen this before, but I'm going to bring it up now. We're going to do the same thing. Busman FC2. Fault current calculator. This is the Busman Series FC squared available fault current calculator. There's an online version right here. It's easy to miss. Don't forget it. Click that. You hit 3-phase. Add to my system. I'm going to add a transformer. And I'm going to say no, assume an infinite bus. We're going to do 1500 kVA, 480 volts secondary. And the percent impedance is 5.75. And we're going to do minus 10%, like I did my hand calculation. Add to the system. I don't want motor contribution. And, doggy. 34,866. 34,864. I'm 2 amps off between those two. So this app helps you, it helps you make life a little simpler. You could add to the system on a secondary. You can add a conductor run. You could add, 500 foot of, how many in parallel? We'll say 10 in parallel. No, we'll say 1. Select the size. 4-aught. I'm just add to the system. There's your conductor, and now you know you're at 6,743. So if you had 500 feet of 4-aught on the secondary of that, which probably would not be enough from an ampacity perspective, but that's not the point. So you have a tool. You have a fundamental understanding of what the tool is doing. It's taking your power system, converting it to impedances, and calculating a fault current based upon Ohm's law. And then we're going to take that number and we're going to compare it against the interrupting ratings of circuit breakers and fuses and short circuit current ratings of equipment. Jason, yes, and you can use that for 70. Let's go back up. I heard a bunch of, I got 110.9, I got withstand. I got the will of fuse. So then, 70B comes into play really for components of electrical systems. If a fault takes longer to open the breaker, wire insulation, dielectric of wire insulation, etc., all absolutely, and all your components, all your terminations, Robert, the stress that's placed on the power distribution system because of fault currents, the longer you let those fault currents flow, the more stress you're putting on the system in general. We already talked about a minimum short circuit current rating, 5 kA for breakers and fuses. David, I would argue, yeah, I think you're okay. I think for a fuse, the minimum is 10K. For a breaker, it's 5K if it's not labeled. But as I said, in fact, if I go to, let me do this real quick. I'm going to call up UL standard for 508. If I go to UL, boy, my throat is killing me. UL 508A, I'm just going to grab this and go Control F. It's not there. Hold on. I know there's a table in here. I go from pages. I'm looking for, I'm looking for a table, and I'm looking for a table that talks about the default assumed short circuit current ratings for components that you'll see in an industrial control panel. And I'm looking. Whoop. Nope. Man, I know it's in here, David. Give me a second. I know you're in here. I know you are in here. Let me search for short circuit. Short circuit current. The short circuit current rating. Here we go. Found it. All right, so this is table SB41. And if you look at the assumed maximum short circuit current rating for unmarked components, 1 kA is a mercury tube switch rated 250 volts or less. 3.5 for a mercury tube switch rated 250 volts or less. Here's your receptacle type GFCI is 2,000 amps. Other than a GFCI is 10,000 amps. Switch unit is 5,000 amps. Terminal blocks are 10,000 amps. I don't see a switch other than a mercury tube type is 5,000 amps. So this is a good table to give you some info on some default values, because we have to do an equipment evaluation after we do our fault current study. Eric Hammond, would it be that the upstream overcurrent protected device providing the... Yes, they work together. So the short circuit current rating, an AIC rating is an interrupting current. So I could have a series rated system to where they both operate together and the upstream device is clearing the fault while the upstream device may be clearing the fault. Short circuit current rating works a similar manner where the short circuit current, if you think about the available fault current, if I drew a waveform, if I drew a waveform and said, here is my current, right, that's passing through a piece of equipment, if I would see this peak value, that first half cycle is a doozy. But a current limiting device will typically do something like this. So the equipment never sees this peak value. The equipment sees that peak value and the duration of the current passing through that equipment is very small. So I'm effectively protecting the downstream or protecting the equipment because of that. Does a GFCI have an AIC? No. Oh, it does. And remember, a GFCI will interrupt currents, but the interrupting, Dawn, is very small because the AIC, the normal current that it's supposed to interrupt is what, around, it'll be 4 to 6 milliamps, but it'll be a ground fault current. That's a freaking good question. Wow, Dawn Kinnear, you, 943. 943, I'm going to Control F, interrupt. Don't search interrupting. I'm searching the standard. I'll bet you that they assume it's really small. Ground fault circuit interrupter shall have necessary interrupting capacity, is what it says there. The device conducts the test current. No. Oh, man. And the short circuit test, I'll tell you the other thing about the short circuit test is that the short circuit test is optional, and you have to have a ground fault circuit interrupter shall not become a shock or fire hazard when operating while in an abnormal condition, such as a short circuit or open circuit component. Each component was likely to risk blah, 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 blah. A single layer. I don't know the answer to that question, Dawn, but that is a very good question. I know it has a short circuit current rating. I'll have to do some homework. Man, Dawn, you come up with the best answers to the quiz questions. Oh, you can't hear me, but I think you fixed that. Already talked about that. Is Mr. G the 7-footer chopped in half of a Latino hillbilly whose thirst for knowledge exceeds my limitations? You are hilarious, man. VARS. Power triangle for the win. Yes. Eric Hammond, infinite bus calculator is great for equipment and device evaluations. Absolutely right. That's a link to default chart for unmarked components. Yes. Don't forget to like and subscribe. Thanks, Laurel. I count on you every time. Jason Doty, I like the real and reactive. You're absolutely right. The foam is the reactive component. The VARs, based on UL 50882. Yes. Does sum of resistance play into why the length limit on the AFCI branch circuit found in 210.12? Freddie B. The length is about the impedance of that circuit. Don't even get me started on how that calculation, because the calculation doesn't match the research that was done. But yes, it's the resistance and reactance of the conductor length. The circuit lengths, yes. Absolutely, Jason. Love it. SB4, yep, there it is. Thank you. You guys were telling me Hey, thank you, Michael Hofkin. I've got a roll too. It's 110. I'm over. Is a hot to ground fault. It will have to open the available fault current unless it is assumed. You're actually right, absolutely right, Don. And I'll tell you what, the circuit that is actually used to do the short circuit test doesn't use a breaker. It uses a fuse, a 20 amp fuse instead of a 20 amp circuit breaker. So the only way to get that thing to pass the short circuit test in general is to put a 20 amp fuse in front of it. And this is taken out of the practical application guidelines for the ground fault circuit interrupters, PAG 9.43. So, hey Tom, our lightning protection system connection to 23. The lightning protection system shouldn't affect that. It's completely separate because it connects to the ground of the system. I would not see that impacting the available fault current or the calculations at all because it's an independent system. Hey, looking forward to seeing you, West by God, Virginia, too, Ryan. Can't wait for you to be here, brother. And hopefully we can go live while you're here. Thanks, Dawn. I really appreciate it. Willie Snyder, he may be late, but he's worth the wait. And Jason, thank you so much. All right, everybody. I've got to run. My throat is killing me right now, so I apologize for sounding hoarse, but I am, and it is, what it shall be. Thanks, everybody. Doug says, so if the short circuit analysis shows that the available fault current exceeds the SCCR rating of a piece of equipment, can current limiting fuses be used to correct this? Doug, it's going to be hard to do that. What you can do is limit the amount of energy that you'll let through. You can't increase the short circuit current rating, but in my opinion, you can reduce the hazard, but you're not going to get it to be code compliant. That's just the thoughts on that one. All right, Doug, and if you want to talk more about that, please shoot me a note. I'd love to chat more about that. What you just noted. All right. Thanks, everybody. Thanks for what you do for the electrical industry. Thanks for what you do for electrical safety. Remember to stay safe, and please, by all means, stay healthy. I'm not. See ya.